Get the recording going. Let's get started. Get through the material, then we can work on any homework problems you guys want. Okay, so 3.4. 3.4 is focused on thinking about the derivative now as a rate of change. Now this should already make intuitive sense. We've already talked about derivatives this way as a rate of change. The slope of the function tells you how the function's changing. If the slope's positive, that means the function's increasing. If it's increasing a lot, it has a very big positive slope. If the function's not going up or down, then it's not increasing or decreasing, it's not changing, so the derivative's 0. And if the function's going down, the derivative's negative. So the derivative already captures this notion of a rate of change because the slope of the function tells you how the height of the function is changing as the function goes on. Right? Mm-hmm. So, we can use it to discover the rate of change of anything we want to talk about the rate of change now just about. So let's say we look at the area of a circle as a function of the radius. You with me?
Yeah.
So this is a formula for the area of a circle, right?
Mm-hmm.
Where r is the radius. And we could imagine plotting this for every possible radius. And the bigger the radius, the higher the area, right?
Yeah.
So how is the area changing with respect to the radius?
Exponentially with r?
Not exponentially. Take the derivative. That gives you the change variable. So I can take the change in A with respect to the radius.
Mm-hmm.
And what's that going to be equal to?
With respect to the radius, just
2 pi r.
2 pi r.
2 pi r.
Which is straight.
Which is linear. Which we could have expected if you look at that. That's just a parabola.
Yeah.
Yeah.
Right? Kind of. Ignore the left-hand half because there's no such thing as a negative radius. So starting at 0 going on, it's half a parabola. But there you go. That's a change in area with respect to r. So how is the area changing with respect to r when the radius is 5? We'll say 5 meters.
You just plug 5 in.
You just plug the 5 in.
Yeah.
10 pi meters. Okay?
Okay.
So we can do this with just about any function you want. Take some function in terms of some variable. Take the derivative with respect to that variable. And that tells you how the function's changing with respect to that variable. Make sense?
So kind of we're just plugging stuff in now?
Well, we're looking at applications of derivatives.
Gotcha.
Okay, so let's look at another one. Common one that's going to come up a lot and come up a lot in physics. One that we've already seen though. So let S of t be the position of an object at a time t. So S of t gives you the position of the object at some time t. Make sense?
Mm-hmm.
Okay. Then the displacement of the object from t to t plus delta t. So the displacement of the object over some interval of time delta t is given by this. You take its position at the end time minus its position at the start time. That's its displacement over the little interval, right? With me so far?
Mm-hmm.
Yeah.
Okay. And so here's its displacement, and then its average velocity is displacement divided by time. Right?
Yeah.
If it goes 10 meters in 2 seconds, its average velocity was 5 meters per second. Make sense?
Okay.
So, that's its average velocity. Now if we want its instantaneous velocity, then we need to take the limit of this as delta t approaches 0, right?
Yep.
So, its instantaneous velocity, v at time t, is equal to then the derivative of position with respect to time. Your change of position with respect to time is what your velocity is. How your position changes with time, that is velocity. Make sense?
Yeah.
Which is equal to this limit right here, which we've already done before, right?
Mm-hmm.
Furthermore, okay, so that's definition of velocity. Velocity That's the derivative of position with respect to time. Okay. Now, we need to understand the difference between velocity and speed. They almost capture the same exact idea. Velocity has direction to it, speed doesn't. So if I call this way my positive x direction, right now I have a velocity of 1 meter per second. Now I have a velocity of negative 1 meter per second.
But you can't go negative.
But there's no such thing as a negative speed.
Okay.
So speed is the absolute value of velocity. Make sense?
Yep.
Okay. What about acceleration? Acceleration is your change in speed with respect to time. If you're accelerating, then that means you're speeding up.
Mm-hmm.
Now, acceleration also has direction to it, positive or negative, so it's actually your change in velocity with respect to time. So acceleration now is the derivative of velocity with respect to time, or the second derivative of position with respect to time.
Okay.
Because velocity was already defined as the derivative of position with respect to time. Right?
Mm-hmm.
So accelerating, if you're accelerating, your velocity is increasing. If you're deaccelerating, if you're hitting the brake, your velocity is slowing down. Right?
Mm-hmm.
So acceleration has change in velocity with respect to time. And then jerk is the derivative of acceleration. So it's the derivative that you're changing acceleration with respect to time, or the second derivative of velocity with respect to time, or the third derivative of position with respect to time. Jerk, that one's hard for us to have intuition for.
Yeah. But it's just the derivative of.
It's just the derivative of acceleration with respect to time. Okay? So let's use some of these. Problem. Here's our position function. This is in meters. So our position function is, the position of an object is 4.9 times t squared. This is dropping an object. This gives me its position at some time t. With me?
Mm-hmm.
Yeah.
Good. So after 1 second of falling, how far has the object gone?
4.9
4.9 meters.
meters.
Right?
Mm-hmm.
Okay. So a question. How far does the object fall in the first 3 seconds?
Uh, 9.8.
You're just trying to multiply that out, right?
Mm-hmm.
But it's just 4.9 times 9, right?
Mm-hmm.
Good?
Yeah.
So whatever that comes out to. So how far falls in 3 seconds? Okay, we can calculate that real easy. Let's look at another question. What is the velocity, acceleration, and speed of the object at 3 seconds? So after it's been falling for exactly 3 seconds, I want to know what's its velocity, what's its speed, what's its acceleration.
Okay.
With me?
Mm-hmm.
So first off, we need to get a velocity function from this thing. This is its position function. So v of t, if I want the velocity, then that's going to be the derivative of s with respect to t, which is equal to what?
Which is just equal to s of.
Look at this. Tell me exactly what it is.
4.9, no, yeah. 4.9 parentheses t plus delta t squared minus.
Just use the rules that you already know. We don't need to calculate by hand anymore.
Oh, just 9.8 t, right?
Just 9.8 t.
Oh,
To 1 there, if you want to think about it that way. Right?
yeah.
Okay, so that gives us our velocity at any time t. What about our acceleration at any time t?
Just 9.8.
Just 9.8. Acceleration is just the derivative of velocity.
Okay.
So, what's the velocity at 3?
Just 3 times 9.8.
Right, so what is that? 29.4, did I do that right?
Yeah, 29.4.
And what's the acceleration at 3?
9.8.
9.8. Now, to put the units on here, this is meters per second, and this is meters per second squared, but the important part is you know how to calculate those numbers. Oh, the speed. What's the speed of the object after 3 seconds?
Just the absolute value of 9.82, right?
9.8.
Oh. 29.4.
It's just 29.4 meters per second.
Why?
Speed is the absolute value of velocity.
Oh, okay.
Velocity and speed give you almost the exact same thing.
Okay.
Only difference is velocity has a direction to it. Let me give you an example where this becomes really important. Let's say I walk this way at 1 meter per second for 5 seconds, and then I walk this way at 1 meter per second for 5 seconds. So I'm back where I started, right? What was my average velocity over that whole trip?
0.
0. What was my average speed?
1 meter per second.
See the difference? Okay. Okay, so let's look at another example now. A bit more involved example and calculate some things. So what is this example? Here's a scenario we're setting up. A piece of dynamite goes off. There's a rock that gets launched up in the air. It's going to go straight up in the air, fall back down, and come back down to the ground. Okay? It's launched up into the air at 160 feet per second. You with me?
Mm-hmm.
This equation gives me its position as time goes forward.
Okay.
Its height in the air is given by this equation. It's just going straight up and then comes back down. That's all it's happening. Okay, so we're going to calculate a few things. First thing we're going to calculate is the max height that this function reaches. How high does that little rock go if it starts out shooting up in the air at 160 feet per second?
It depends on your seconds, right?
Well, we'll calculate it. Now, what do I know about an object's speed when it reaches its highest point?
So that stands still.
It holds still, right? It starts out going really fast and slows down, slows down, slows down, slows down, slows down, stops, and then starts coming back down.
Yeah.
Yeah.
So, when it's at its max height, its velocity is
0.
0. So when is its velocity 0? Let's figure that out.
Okay.
Okay.
So what does a velocity function look like?
Just. Don't you have to find the derivative of
160 minus
32 t?
32t.
Perfect.
Okay.
So if I set this 0 equal to 0, 160 minus 32t, I want to know when the velocity is 0, right?
Oh, and then it's just simple algebra.
Then it's just simple algebra. So 32t is equal to 160, or t is equal to, dividing by 32, and what is that, 5?
Yeah.
So at t equal to 5 is when we reach our max height.
5 seconds. Okay.
That's when. But what is the max height?
Oh.
We have to come plug that back into here.
Okay.
Plugging the 5 back into there, right?
Yeah.
Okay.
Does that make sense why?
Mm-hmm. Yeah, I see what
This is when it reaches the max height. Now we need to calculate what that actual max height is. So we need to calculate s at 5 seconds. So, let's calculate that. So 160 times 5 minus 16 times 25, right?
Mm-hmm.
Okay, so what's 160 times 5?
800.
800. minus, what's 16 times 25? How many 25s in 100?
4.
4 of them. So how many hundreds is this?
400.
So it reaches a max height at 400 feet. Good?
Mm-hmm.
All right. Now we want to find the velocity and the speed when s is 256 feet, or in other words, when it's 256 feet in the air.
The speed?
Yeah. How fast is this thing moving when it's 256 feet in the air? Now notice it's 256 feet in the air twice. Right?
On the way
Yeah.
up, way down.
On the way up and on the way down. Exactly. So we got to calculate two speeds here. So first off, when is it 256 feet in the air? How are we going to figure that out? I need to know when s of t is equal to 256.
Yeah.
Right?
Which is the
So I need to solve the equation. 256 is equal to 160t minus 16t squared.
Okay.
Why?
Here's s of t. And I need to know when it's equal to 256.
Oh, yeah.
So, sorry. My ear needs to pop, it's driving me nuts. Won't go. So let's see, 256, I just happen to know that that's the same thing as 2 to the 8.
So why are you factoring it out like that?
I'm going to divide it by 16. I'm going to divide everything by 16.
Okay.
16 is the same thing as 2 to the 4.
And then 2 to the...
So 2 to the 8 divided by 2 to the 4, it leaves me with 2 to the 4, or in other words, 16. So when I divide by 16, we get 16 is equal to 10t minus t squared.
Okay.
Follow that?
Mhm.
Okay. I'm going to put everything on this side, make it equal to 0. So we have t squared minus 10t plus 16 is equal to 0. Follow that? And now we just factor it. What do I need? I need two numbers that multiply together give me this, and added together give me this.
8 and 2.
8 and 2, negative. Negative 8, negative 2 equals 0.
Okay.
So, t equal 8 and 2.
Those are the 2 seconds.
Those are the two times where our height is 256.
Okay.
Okay.
Right? So now I need to find the velocity at these two times.
Mm-hmm.
Remember, I'm looking for the velocity and the speed when the height is 256 feet. When is the height 256 feet? At 2 seconds and at 8 seconds. So I need to find the velocity at 2 seconds and the speed at 2 seconds, and then the velocity at 8 seconds and the speed at 8 seconds.
Okay.
Alright, so what's our velocity function again?
160 minus 32t.
So our velocity at 2 is equal to
160 minus
64. Which is, yes, 96.
feet per second. So that's both our velocity and our speed.
Yeah.
Now our velocity at 8 256. Let's see, 8 is 2 cubed, and we're doing that times 2 to the 5 is 2 to the 8 is 256, yeah.
Okay.
what does that equal? Negative 96 feet per second.
So speed stays the same.
So the speed's the same, the velocity just changes directions.
Yep.
But it's the exact same speed. Because it's slowing down, slowing down, slowing down, slowing down, going up still, the first time we reach it. Goes up, stop, now it's coming down, and then speeding up as it goes down.
Okay.
Make sense?
Mm-hmm.
So, calculate that one. What's the acceleration?
Just the derivative of that, right?
Just the derivative of
So
velocity.
it would be 32, negative 32.
Negative 32. It's just negative 32 feet per second squared.
Okay.
Right?
Mm-hmm.
Lastly, let's figure out the time that the rock is in the air total. So the rock shoots up in the air, eventually comes down, lands back on the ground.
Okay.
So when does that happen? How do we figure out when the rock lands on the ground again? When do we know when it hits the ground?
Its velocity and speed are 0.
No.
Yeah, but that's because the ground interferes with it. The instant it hits the ground, its velocity isn't 0. What's 0 when it hits the ground?
Its position.
Its position. So we want to know, when is this 0?
Okay.
SFT is it? Yeah, it is. Okay.
Yeah. So we want to know when 0 is equal to 160 t minus 16 t squared. Divide through by 10, or divide through by 16. That's the same as when 0 is equal to 10t minus t squared, right?
Mm-hmm.
Factor it. We can pull out a t out. When is that equal to 0?
When
T is equal to
T
10.
is equal to 10.
And
10 seconds.
when else?
And when T
It's
is
equal to 0 twice. 0 and 10, right?
Mhm.
So what that's saying is, at 0, right when the dynamite goes off, it's on the ground, and then 10 seconds later, it's back on the ground.
Okay.
So what was the time of the flight?
10 seconds.
10 seconds, exactly. Good?
Yeah.
All right, so that's the type of problems that you'll get for 3.4. Now on to 3.5, trig functions. Derivatives of trig functions. Now, I have them all written out here. We'll calculate each of these. They're all real easy to calculate, so it won't be too bad. But the derivative of sine of x is cosine of x. The derivative of cosine is negative sine. The derivative of tangent is secant squared. The derivative of secant is tangent times secant. Derivative of cotangent is negative cosecant squared. And derivative of cosecant is negative cotangent times cosecant.
Do we prove any of these?
Yeah, we're going to do all of them real quick.
Okay.
So, start with sine. So what is the derivative of sine? That is the limit, as we'll use the author's notation, h approaches 0 of sine of x plus h minus sine of x all over h, right?
Yep.
Now we need to use our sum of angle identity for sine. So sine of x plus h, that's the same thing as it's sine of the first times cosine of the second plus sine of the second times cosine of the first. That's expanding this out. And then we need to do minus sine. Minus sine of x all over h. With me?
No.
Yeah.
How'd you get the cosine of h? And the cosine of x again.
This, right here. This,
Yeah, I'm saying how did you convert it?
This is the rule.
it's the sine of alpha plus beta is equal to sine of alpha times cosine of beta plus sine of beta times cosine of alpha.
Yeah, I remember that. Okay.
That's what I used on this to get this term and this term.
Okay, I see how you did it.
Okay. Which is equal to, now we just got to group these in ways that we know how to calculate it. So I'm going to factor out of the two terms with the cosine. Oh, no, I'm not. I'm going to factor out of these two terms a sine of x. So I'm factoring the sine of x out of this term and this term, which leaves me cosine of h minus 1. So that's these two terms, and then I still have this term. Plus cosine of x times sine of h. This is over h. This is over h.
Okay.
With me? Okay, now I know how to calculate the limit. The limit of cosine of h minus 1 over h as h approaches 0 is?
Is it not 1?
No, it's 0. And sine of h over h is?
1.
Let me write this one more time. Maybe this will help you see it all. Oops, forgot my limit. Limit as h approaches 0 of sine of x times cosine of h minus 1 over h plus cosine of x times sine of h over h. Right?
Mm-hmm.
So this is 1, and this is 0.
Which is just cosine of x.
It's just cosine of x.
Okay.
Good?
Mm-hmm.
Any questions on that? Alright, so that's sine. Cosine similar, and then the other ones are a lot easier.
Okay.
So with cosine, we have, we're looking at cosine of x plus h minus cosine of x all over h, right?
Mm-hmm.
Now we got to use our identity for cosine for the sum inside of a cosine. So that is equal to cosine of the first angle times cosine of the second angle minus sine of the first times sine of the second.
Is that right?
Yep. And then minus cosine of x. All right.
Then same thing.
Then same thing. So I'm going to factor cosine of x out of these two terms, and then we should be able to calculate our limit. So this is equal to cosine of x times cosine of h minus 1 all over h minus sine of x times sine of h over h. Follow the algebra?
Yep.
Now I take my limit. This becomes 0. This becomes 1. And I'm left with
Negative sine of x.
negative sine of x. Follow that?
Yeah.
Okay. So that's sine and cosine. And now remember, everything else can be expressed in terms of sine and cosine, so the rest are easy. So now let's figure out the derivative of tangent.
Okay.
Well, the derivative of tangent, that's the same thing as the derivative with respect to x of sine of x over cosine of x, right?
Mm-hmm.
And we know how to take the derivative of a quotient now. So we don't need to go back to the definition of a derivative directly. We can use our derivative rules. What's the derivative of a quotient? The bottom times the derivative of the top minus the top times the derivative of the bottom, all over the bottom squared.
Can you write that down?
The derivative with respect to x of f of x, well, of f over g is equal to the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared.
Okay, I remember that.
Okay. So that's our formula. You need to memorize this, by the way. You use it so much left and right, you can't be struggling to know, to remember what the quotient rule is or what the product rule is. So, let's do it. So we have the bottom, that's cosine of x, times the derivative of the top. What's the derivative of sine of x?
Cosine.
Cosine of x. So the bottom times the derivative of the top minus the top times, what's the derivative of the bottom?
Negative sine of x.
Negative sine of x. All over the bottom squared. With me?
Mm-hmm.
Which is equal to cosine of x times cosine of x is,
Cosine of x squared.
so that's cosine squared of x minus sine of x times minus sine of x gives me,
Sine squared of x.
Positive sin x.
so cosine squared plus sine squared is
1.
1.
Yep, I remember that.
1 over cosine squared of x,
And that's
which is the same thing as secant squared of x.
Okay.
What's secant mean?
1 over cosine.
Okay.
Will you let me and Jeremy prove some of these?
Sure. Do the next one.
Okay. You want me to do it up there or just on my paper?
You want to do it up here? You can do it up here.
Why do I get to walk it through with me?
So you're doing secant.
What is secant? 1 over.
1 over cosine.
Yep.
You're gonna need to write a little bigger.
Can you not see that?
Well, I can barely see it.
Okay. Well, you can just come up here with me because you can do the next one anyway. Which is just 1 over negative sine of x, right? Did I do that right?
Whoa, whoa, whoa. No, you did not. Use your rules. Derivative of the bottom.
Low to high
Okay.
times high to low.
The top times the derivative of the bottom minus the bottom times the derivative of the top.
Square the bottom and off you go.
That's right. Negative sine of x.
Bottom times the derivative of the top.
So
I'm sorry, I
just
said it
normal
weird before.
cosine.
He did say weird before. It's
Sorry. So
Cosine
bottom
of
times
x.
the derivative of the top is what?
times, the derivative of 1 is just 0, right?
Right.
That's an easy one.
Minus 1 times negative sine of x all over cosine squared of x.
Perfect.
Okay? That's just
Sine of x.
sine of x over cosine squared of x.
Uh-huh.
And what is that?
Well, split that cosine of x into 2. So write that as sine of x over cosine of x times 1 over cosine of x.
Sine over x.
Write that as sine of x over cosine of x times 1 over cosine of x.
Because secant is 1 over cosine of x, and the sine of x and cosine of x cancel out, right?
What is that? That's tangent. What is that? And that's secant.
Oh,
You're
what
done.
the heck?
Oh, I am done. Yeah, that one was super easy.
Told you, they all are. All right, you up, Jeremy?
We'll see.
So calculate the derivative of cotangent now. That's
Okay.
cosine over sine.
Okay. That's awful deep. Cotangent. What am I doing? Sine over cosine. No.
No, that's tangent.
Cosine over
Cosine
sine.
over sine. Wait. It's equal to
Factor negative out of your numerator.
okay.
He can leave it, can he not?
Like that. And then just continue.
Yeah. No, 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 no.
What am I missing?
You can't do that.
Can you not just take
I
the...
have 6 plus 6 over 6. That's 1/2, right?
Yeah.
I can't cancel like this and say, oh, so it's equal to 6. But what is sine squared plus cosine squared?
1.
1.
Which is...
Perfect.
Okay.
Stick with me.
Yeah, you can only cancel out factors from the numerator and denominator. You can't just cancel out terms.
Yeah.
Okay. And I don't think we need to see the last one. You see how to do these.
Yep.
So there's the derivatives of your trig functions. Not bad at all, right?
It's alright.
So now let's do some examples where we take the derivatives of the things that have trig functions. So let's take this derivative really quick.
Okay.
What's the derivative of this?
2x minus cosine of x.
Perfect.
Yep, I see him.
All right. Next, let's do the derivative of this.
2x.
That's a product of two things. So
Oh.
be careful. We have to use the product. So
Okay.
derivative of the first multiplied by the second plus the derivative of the second multiplied by the first.
Yeah.
Is it not minus?
No, it's plus.
Okay.
So the derivative of the first gives me 2x. The derivative of the first multiplied by the second plus the derivative of the second multiplied by the first.
Okay.
So 2x sine of x plus x squared cosine of x.
That's your answer?
Yep.
Alright.
Okay. Let's look at the derivative of the next one.
Okay, that's
You tell me.
1 times
Bottom times the derivative of the top.
Yeah. X times cosine of x. Minus
1.
Minus.
Wait,
Yeah, minus 1. Or just sine of
Sine
x.
of
Sine of
x.
x. Yeah, times sine of x. All over.
x.
There you go.
Okay.
That's the answer?
Uh-huh.
Okay.
5 plus 5 minus sine of x.
Perfect.
Cosine.
Cosine of x
Times the derivative.
times cosine of x.
Derivative of the first multiplied by the second plus
Derivative of the second, which is negative sine x. Multiplied by sine x.
So we get cosine squared of x minus sine squared of x.
Okay.
Wouldn't that just equal -1? Or does that not work?
No.
So it's only when it's plus?
Yeah.
Yeah. Is that?
Okay. And now let's do this one.
1 minus sine of x minus sine of x multiplied by sine of x. Negative sine of x. That's the one.
Minus cosine of x times.
Just negative cosine x.
What? Where'd your 1 go?
What's the derivative of 1?
Oh.
All over
1 minus sine of x squared.
perfect. So good back to this out, I guess. Minus sine of x plus sine squared of x plus cosine squared of x all over 1 minus sine of x squared. Did I do that right?
Mm-hmm.
Sine of x plus cosine of x, that's just 1.
1.
So I'm going to write the 1 first. So we get 1 minus sine of x over 1 minus sine of x squared. Cancel one of those out with that. So just 1 over 1 minus sine of x. Okay. So there are some examples taking derivatives with our different trig functions. Let's move on. Make sure I move the camera. Oh, I'm on it right here. Okay. So, one more problem with oscillating motion. So, here's the problem that we're setting up. I've got a weight attached to a spring attached to the ceiling. With me so far? Now, what I'm going to do is I'm going to take this weight and I'm going to press it up so it's 5 centimeters away from where it started. And then let it go.
Okay.
So what's going to happen as I let it go? it's going to go up and down like this, right? So the spring, if we were to kind of plot what this looks like a little bit, it's going to start up here at 5, and then it's going to fall down to -5, and then bounce back up to 5, and then back down to -5 like that.
Doesn't it start to slow down though?
We're going to assume a perfect system so it doesn't lose any friction, never slows down,
Okay.
perfectly oscillating back and forth. Good?
Mm-hmm.
So notice its position then is given by 5 times cosine of t. Notice as 0, what's cosine of 0? 1. What's 1 times 5? 5. So it starts out up here,
Okay.
and then it's going to go down and up and down and up. And it's going to follow just like a cosine function.
Okay.
So here's how this is how its position is changing with time.
Yeah.
We want to calculate now its velocity and its acceleration.
Okay.
So now what is the velocity of this function?
0.
What's the derivative of cosine? With respect to, what's the derivative of this with respect to t?
Doesn't matter what it is because the 5 goes through 0 and it's multiplied by whatever that is.
Yeah.
So if I have 5x to the 6, what's that thing's derivative?
You're right.
30x.
30x, not 0.
Yeah, but you're multiplying 5.
It's just
By
the
x to the 6.
coefficient.
It's just a coefficient.
Okay.
I'm still confused.
The derivative of a constant is 0. This is not a constant. This is not a constant.
Only works if it's plus or minus.
Yeah, it has to just be a constant if its derivative is 0. Now it's not a constant. It's all over the place.
Okay.
Okay, I see it.
Okay, so once again, what's the derivative of this?
It is 5 times negative sine of t.
Minus 5.
Yeah, minus 1.
Right? And what's the acceleration?
It's just
Acceleration is
minus 5 cosine of t.
Perfect.
yep.
So that's how you calculate its velocity and its acceleration at any given time.
Okay.
Good?
Mm-hmm.
Yeah.
Okay. Next, calculating multiple derivatives. So y equals secant of x, I want to find y double prime. So not its first derivative, but its second derivative.
Okay.
Well, we already know what y prime is. Right? What is
The
it?
tangent of x times the
Times the
secant of
secant
x.
of x.
Yeah, secant of x times tangent of x. So now I'm trying to find the derivative of this. That's what y double prime is.
Yeah.
Which is just
So y double prime is equal to the derivative of the first multiplied by second. So what's the derivative of secant?
it's just tangent x times
Tangent
secant
x times
Secant x times tangent x. So the derivative of the first multiplied by the second makes that tangent squared.
Yeah.
Plus the derivative of the second multiplied by the first. What's the derivative of tangent?
Secant squared x.
Times secant.
Secant cubed x.
3x.
There we go.
Fun.
Okay.
Okay, now on to the chain rule. What is the chain rule? The chain rule is going to be the last of our major derivative rules. So this is kind of like the product rule and the quotient rule. Now we have what's called the chain rule. The chain rule tells us how to work with functions where you can view them as functions inside of functions. So let me give you an example of one that we've used a chain rule to solve. Here's an example of one that we've used a chain rule to solve.
Okay.
notice that if I let u equal 5x cubed minus x to the 4, then I can rewrite this thing as u to the 7. So it's like it's a function inside of a function.
Okay.
Or, just to drive it home, if I say g of x is equal to 5x cubed minus x to the 4, and I say f of u is equal to u to the 7. With me so far? We'll keep x's here. Then this whole thing is f composed with g of x, right?
Yeah.
That's what this is. So, this we can always view it as a function inside of a function.
Like function composition.
Function
Okay.
composition, exactly. So if I know how to take the derivative of a function composition, I now know how to handle cases like this.
And what, you just split it into multiple functions?
Well, the rule is the derivative of the outside multiplied by the derivative of the inside. That's what we'll show.
Okay.
So there's a rule for doing it. Here's the rule for doing it right here. If you have f composed with g prime, if you're taking this derivative, the derivative of that, then that's going to be f prime of g of x times g prime of x. That's going to be the rule that we come up with. So just really quick plugging that in here, just to see it in action once. Let's say it real quick. So that would be equal to f, remember, we're viewing this as f of x is x to 7 and g of x is the inside one, right?
Mm-hmm.
So this would be, let's see, what's the derivative of
7x.
7x to the 6.
Oh, 7x to 6.
So we have 7, and now instead of x, we have g of x. So 7 g of x to the 6. G of x is this thing. So 7 g of x to the 6 times g prime of x, the derivative of g now, which is just 15x squared minus 4x cubed. That's the rule we're going to prove.
How is that helpful for finding that? Oh, that is the derivative.
That's the derivative.
Yeah. Okay.
Good? So let's prove it really quick. So we're looking for the derivative of this thing. So
Are they going to want us to multiply the 6 into the...
yeah, you're going to need a, it depends on what you need to do. It depends. Sometimes it's nice to distribute it, sometimes not. In this case, we didn't want to distribute this whole thing out to find the derivative. So you could probably leave it just like this and be fine. That's a pretty good way to leave it. Now, that's way better than multiplying this whole thing out first and then taking the derivative the way you know how.
Yeah.
That would have been massive.
Yeah.
Okay. So let's do it. So we want the limit as x approaches x naught of f of g of x minus f of g of x naught all over x minus x naught. Right?
And you could have done it the author's way too, right?
Yeah.
Saying it doesn't matter which way you choose to go about proving it, you can still come to the same conclusion.
Yeah. So the trick to this is multiplying top and bottom by f of x minus f of x naught.
Why?
Because now, in the denominator, I'm just going to swap these two terms. So this is equal to the limit as x approaches x naught. Oops, not f of x, g of x.
Okay.
G, 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 G. Okay, so now that's equal to f of g of x minus f of g of x naught all over g of x minus g of x naught times g of x minus g of x naught all over x minus x naught. Right?
Okay.
So we're almost done. Notice that we already know what this is, g of x minus g of x naught over x minus x naught. We know what the limit as x approaches x naught of this thing is, right?
What is it?
It's just g prime of x naught.
Okay.
I don't see it.
What is g prime of x naught equal to? By definition, it is the limit as x approaches x naught of g of x minus g of x naught over x minus x naught. That's the definition of a derivative. For anything.
Yeah.
That's exactly what you have right here.
Okay.
First, yeah.
So the right hand term is just g prime of x naught.
Mm-hmm.
I see how you did this then.
Okay, so it's this left-hand term that's giving us grief. We need to figure out how to work with this left-hand term, right?
Yeah.
Now, if we could rewrite it like this, I'm just going to do it and then we'll think about it later. If I could just rewrite it like this, the limit as g of x approaches g of x naught of f of g of x minus f of g of x naught all over g of x minus g of x naught times the limit as x approaches x naught of g of x minus g of x naught all over x minus x naught. So if I can write it this way, we know what this is. This is just g prime of x naught.
Mm-hmm.
What would this be though?
F prime of g of x naught.
F prime of g of x naught. So the only question is can I replace this limit as x approaches x naught with g of x approaches g of x naught? Are those the same thing? Is it true that as x approaches x naught, g of x approaches g of x naught?
Yes.
The answer is yes. If g is differentiable at x naught, then it is also continuous at x naught. You remember that? If it's differentiable at a point, it's continuous at a point. We did that proof last week. And what does it mean to be continuous? A function is continuous at a point if the limit as x approaches x naught of g of x is equal to g of x naught. That's what it meant to be continuous.
Yeah.
So the limit as x approaches x naught, g of x approaches g of x naught. So this limit and this limit are the same thing. As x approaches x naught, it is true that g of x approaches g of x naught.
What if it's a constant?
If g is a constant,
Yeah.
it still works. Doesn't matter what g is.
Okay.
So, this was the only little holdup. And now that we have that, then we're done. So this is the same thing as f prime of g of x naught times g prime of x naught. Which is what we were after.
Yeah.
Okay. The book has another way of showing this using Leibniz notation. And the book's way of doing it, you need to think about the u being an inside function. So we do u is equal to the g of x that we used in this case, and we're still doing the exact same thing. With me?
Yeah.
So then they say we want, except for they're going to call the whole function y. So u is equal to g of x, y is equal to f of g of x. With me?
Yeah.
Yeah.
Okay, so we want the derivative of y with respect to x. Right?
Okay.
Which is the limit as delta x approaches 0 of delta y over delta x. Right?
Yeah.
Now we let delta u is the change in just this part of the function when x changes by delta x.
Okay.
So I'm going to multiply this top and bottom by delta u. With me?
Yeah.
So this is now equal to the limit as delta x approaches 0 of, swap my terms a little bit, delta y over delta u times delta u over delta x. With me? And then, if we can finally just replace this, if we can write it like this, the limit as delta u approaches 0 of delta y over delta u times the limit as delta x approaches 0 of delta u over delta x. Then we can take our limits. Now, it's true that as our change in x goes to 0, so does our change in u.
For the same
Because
reason.
g is a continuous function for the exact same problem. So this is equal to the derivative of y with respect to u times the derivative of u with respect to x. So dy dx is equal to dy du times du dx. Okay?
Okay.
So let's write out a function now using that formula, and let's solve it again. Let's do this exact problem again, seeing how it's using the formula. So I know that dy dx is equal to dy du times du dx. And let's look at this function. So my u is going to equal 5x cubed minus x to the 4, right?
Yeah.
So, if I rewrite y in terms of u, then y is equal to u to the 7th. So dy du is equal to
7 times u to the power of 6.
7 times u to the power of 6. 7 times u to the power of 6. Now remember that u was this thing, 5x cubed minus x to the 4. So that's dy du.
Okay.
And now we need to find du dx. What's du dx?
It's just
Just the derivative of that. Just our 15x squared minus 4x cubed.
Yeah.
Put it all together, so now dy dx is equal to dy du times du dx.
Yep.
So same thing we've already been doing. Or the derivative of the outside function multiplied by the derivative of the inside function is the way I'll always say it. Okay?
Okay.
Hey.
So let's go through these examples, come back to these ones, and then I think you'll have it. So let's look at this one. F of t is equal to cosine of t squared plus 1. Let's take the derivative of that.
Okay.
So f prime of t is equal to the derivative of the outside multiplied by the derivative of the inside, plus the derivative of this thing, of cosine.
Why do you need to use that? Well, where's the two formulas?
There's a t squared in there.
And that's the inside?
Mm-hmm.
Okay.
So, what's the derivative of cosine?
Negative sign.
So we have negative sine of t squared.
Yeah.
Now we need to multiply by the derivative of the inside,
Which is 2t.
2t. So it's equal to negative 2t times sine of t squared.
Okay.
Alright. Let's do another one.
Okay.
Let's write it really explicitly if we want. So my f of x, oh, I already called that thing g of x, shoot. So we'll say u is equal to x squared plus x, and y is equal to, if we write y in terms of u, y is equal to sine of u, right?
Mm-hmm.
Okay, so let's calculate the derivative. What's dy du?
It's the cosine.
Cosine of u.
It's cosine of u. So dy du times du dx.
2x plus 1.
Perfect.
Okay, I'm starting to see it.
Assuming that's a plus.
Yes. Good.
Yeah.
All right, let's do the next one. Next one, we have 3 of them. We have, here's our outer function, and then we have this function, and then we have 2t inside of that.
How does that work?
So now we can say that y is equal to, let's work backwards. We usually use a w next. So w is equal to 2t, u is equal to 5 minus sine of 2t, and y is equal to
Tangent of u.
Tangent.
tangent of u, right?
Yeah.
Can you?
So dy dx is equal to dy du times du dw times dw dx. Notice the dw's go out, du's go out, and you're left with dy dx.
What?
Yeah.
Just seeing how this and this are the same thing.
Where
You
does-
really shouldn't think about it that way yet. We'll get to differentials, but anyways, just notice that is the pattern when you do it.
That's a multiplication, not a minus.
This is a multiplication.
Okay.
This is a multiplication.
Okay.
Okay? So now let's calculate this thing. So dy dx is equal to dy du. What's that?
The secant squared of 5 minus sine of 2t.
Oops, I shouldn't have 2t
Of
there, I
W,
should have w.
yeah.
But yeah, so secant squared of u. So that's dy du times, now we need to do du dw.
It's
It's just negative cosine.
Negative cosine of w times dw dx.
Doesn't the
Oh, this should all be dt. Sorry. Our variable's t.
doesn't the why is the 2t still there? If you took the derivative of w from u, wouldn't that give w to the power of 0, which is just 1?
What are you talking about?
When you're going from du to dw.
Are you saying calculating this one?
Yeah.
So right here.
Why? But you use the formula 5 minus sine w. And if you're,
Oh, I'm just plugging in my w as 2t. I could have left that w if you wanted.
but wouldn't the w disappear? Like, because it's to the power of 0 now?
it's not.
No. No.
2t
Because you're finding
That is
the
a term that you're passing into the sine function. That is the same thing as sine of x. What's sine of x?
Oh,
When we take its derivative?
I see your point.
Okay, good.
Yeah.
Any other questions?
I think we're good.
So what's this term now?
Uh,
We're still missing one. It's 2. Okay, so there's our derivative.
Looks good.
so if you really wanted to like calculate what t was, you would just plug it in and it would all come out. However it came out.
This is delight. I don't know what you mean when
He's
you
saying
calculate
if
what
you're
t
trying to
is.
find a t.
Oh, find the value for a particular t. Yeah, just plug it in. Okay, so let's continue. This one we've already done, so let's do this one.
Okay.
Now, another way that we can view this, to see how it's using the chain rule, we already know how to calculate this using the quotient rule. But if we want to use a chain rule instead, the way to view this is it's 3x minus 2 to the negative 1.
Okay.
Now it's chain rule, right?
Yeah.
So let's calculate it. So what is the derivative of this with respect to x? Take the derivative of the outside. So what do I get?
The derivative of the outside?
Yeah, so we have a function inside of a function, right? Our outside function is x to the negative 1. Our inside function is 3x minus 2.
What is
And you're just doing that all in one go?
Yeah,
What is negative 1
Okay.
being derivative?
so what's the derivative of x to the negative 1? Bring it down, subtract 1.
So it's negative 1.
So
Negative
it's
1x.
Negative 1
2.
times x
3x.
to the negative 2
Okay.
times the derivative of the inside.
Times 3.
There you go.
Okay.
A lot easier than the quotient rule.
Yeah.
So you could start doing like the quotient and the multiple using this chain rule?
Sometimes, yeah.
Why not all the time?
Well, it just depends on what the problem gives you, whatever's easiest with the problem you're given. I mean, in this case, it's easy to view this as a negative 1. We could have just as easily had a 10x cubed up here, and now it's not. It's easy to view that as a function inside of a function. I'm sure there's still a way to solve it using the chain rule, but don't hurt your head trying to come up with a way to think about it that way. Just solve it however it's easiest. All right, let's solve this one. Well, it's the derivative with respect to x of sine of x to the 5.
What would be
Is
your
this-
two individual functions in that?
Let me write this another way. This is the same thing as sine of x to the 5.
Okay.
So it's just your
It's cosine of x to the 5.
4, no,
Now,
5 sine of x to the power 4
5 times the sine of x to the 4 multiplied by,
5 to the power 4.
no, just cosine of x.
Cosine of x. Yeah.
Okay.
Derivative of the outside multiplied by the derivative of the inside. What's the derivative of this thing? That's 5 sine of x to the 4 now times the derivative of the inside.
Okay.
Okay.
You see that?
Yeah, I was thinking about it differently.
Okay, let's do this one now. So we're looking at the derivative with respect to x of 1 minus 2 of x to the negative 3. It's equal to,
Negative 3 parentheses that stuff to the power of negative 4 multiplied by negative 2.
perfect.
Okay.
There you go. Chain rule. Okay, we'll take a break now, and then when we come back, we'll do implicit differentiation, and then we'll do homework.
Implicit, is that 3.5?
I don't know.
I think so.
No, implicit, whoa. We just went through 3 lessons.
Uh-huh.
3 lessons.
Implicit derivatives is 3-7.
So we're doing 3.3, 3.4, 3.5, and 3.7.
We did 3.3, so it's 3.4, 3.5, 3.6, and 3.7.
And we're doing all that for homework tonight, Ronnie?
No. You don't have to have all of it done tonight.
Oh, but it needs to be done before the test, right?
Of course.
Okay. back our chapter 2 test?
Yeah, and your homework.
Okay.
Just at my desk. Ugh.
Are we doing 3.8 and 3.9 tomorrow then?
Yeah.
And so we're taking the test next week?
Tuesday next week, yep.
After this week, it gives us 5 more classes, right?
I have no clue.
Well, you have 3 different classes for section, chapter 4, then 1 class for chapter 4 test and the review, and then the midterm.
We're not, remember that we're not on the same as the academy schedule.
Yeah, I'm saying what, you have it for 5 weeks, right? Not 5 weeks, but 5 class days. So in 2.5 weeks, what do you plan on, do you just plan on going right into
We're
physics?
no. We're finishing all of, there's 6 chapters. Keep looking at your syllabus.
Oh, sorry.
You'll take a final.
Why are we not taking the midterm after chapter 3?
Because chapter 4 is still a lot of the exact same stuff. Chapter 4 is applications of derivatives.
Oh, integrals, right? Oh no, integrals is chapter 5 and 6, right?
Right.
Sorry.
So yeah, the midterm's kind of spaced awkwardly. rather than doing it at the end of chapter 3, we'll do it at the end of chapter 4.
Okay.
Yeah, we still won't be starting physics for a while. Hopefully it lines up pretty well with this semesters.
And then physics is just as long as this, right?
Physics, we have an endless amount that we can do, so.
So we're just gonna go until the end of the year?
Yeah. Ready?
We're getting ready for super.
All right, implicit differentiation. What do we mean by implicit rather than explicit? You're used to being given functions explicitly. In other words, f of x is equal to some function in terms of x. So you already have it expressed that way and you don't need to solve for what it equals. Now notice the equations I have written up here. Y squared equals x. I didn't tell you what y is in terms of x explicitly. You have to figure that out.
Okay.
So if you were looking at this and you're trying to find the derivative of y with respect to x, if you're trying to find dy dx, how would you do that?
Just find the derivative and then square the whole thing. Or did I have that wrong?
I want to find the derivative of y with respect to x of this.
You could just root both sides first.
You'd have to root both sides first.
Oh, I see.
I'd have to write y is equal to plus or minus the square root of x. Right?
So in a sense you have to find.
And so this has two functions in it. So we could look at the function y is equal to the square root of x, and we could look at the function y is equal to negative the square root of x. Why does it have two? Well, if you graph that thing, what does it look like? It looks like this. And so you have to split up into the positive and negative case to have functions, right? But then you can find the derivative of each of these things. What's the derivative of this?
Root of 1.
Right.
It's the same thing as x to the 1/2.
That's the derivative, or?
No, that's the same thing. So what's y prime equal to?
1 to the 1/2.
1/2 times x to the negative 1/2.
What?
Yep.
Bring it down, subtract 1.
Oh.
Right? Which is the same thing as 1 over 2 x to the 1/2, which is the same thing as 1 over 2 square roots of x. This is one that we've already calculated by hand.
Can't you not go into x and 1/2 and just in that root make x equal to 1?
Let's see that whole thing on here. Yeah. What did you say?
Instead of going to x to 1/2, why can't you just in the square root make x equal to 1?
Why can't I make x equal to 1? X is
Because
equal.
you're finding the derivative.
I can view that as x to the 1. That's fine.
And then solve it from there, don't go into the x.
How do you take the derivative of a square root?
Square root of 1 is just 1.
Square root of 1 is just 1, that's true. 1 squared is just 1. I can't just view x to the 1 squared. Oh, the derivative of that. Okay, that's 1. Now square it. Okay, so 1. I'm not sure where backward logic is. You still have to take the derivative of the function. So you have to take the derivative of the square root. The only way to do that is to view it as a 1/2. Anyways, and if we take the derivative of this thing, we'll get the exact same thing. We get y prime is equal to negative 1 over 2 square roots of x. So you know how to take the derivative this way, right?
Mm-hmm.
Now we're going to show you how to do implicit differentiation. Implicit differentiation means I just take the derivative of both sides and I use my chain rule. So we'll see what that means here. Take the derivative of this thing now. Just take the derivative of both sides. So what is the derivative of y squared?
2y.
That's going to be 2y to the 1, right? Times the derivative of the inside, dy dx, times the derivative of y.
That's it. Well, y times okay.
So how do I take the derivative of y squared with respect to x? I want to take the derivative of y squared with respect to x. Okay?
Y squared is equal to x.
Forget that. Y is some function in terms of x.
Okay.
That's what we know.
Okay.
So I want to take the derivative now of y with respect to x. It's the same thing as when you had u squared as your function. And we were taking the derivative of it, what was it? It was 2 times u to the 1 times the derivative of u with respect to x. Now, whatever that is.
Yeah.
Times du dx.
U dx.
Right?
Okay, now I see how you got
Same thing here. So when we take the derivative of 2y, or of y squared, we're going to get 2y times dy dx. With me? Is equal to, so that's taking the derivative of the left-hand side. What's the derivative of the right-hand side?
Yes. The derivative of x.
Yeah, what's the derivative of x with respect to x?
Just 1.
Just 1.
Because it's dx over dx, right?
Mm-hmm.
Okay.
The derivative of x with respect to x. Dx over dx. With me so far?
Mm-hmm.
Okay, so now just solve for dy dx. So then dy dx is equal to 1 over 2y. There's our answer. Now, if you want to solve and get that in terms of x, you can. What is y? It's plus or minus the square root of x.
Oh, I see.
Right? What is y? It's plus or minus the square root of x. Plug in positive x, which derivative do you get? You get this one. Plug in negative x, you get this one. So it gives you the exact same thing.
Yeah, we already did. Okay.
Yeah, that was doing it the way you already knew how. This was doing it with implicit differentiation.
Does it matter which way you do it?
No, of course not.
So, why would you do it implicitly?
It's easier.
Because, so that was a simple one. But now let's look at one like this. Do you want to solve that thing for y and then take the derivative? Or should we just take the derivative?
I guess we could just take the derivative. But
Yeah,
that
so
one
you
isn't
can
that
take
bad.
you can spend your life solving all these for y first and take the derivative if you want. And work out all the algebra. That's perfectly fine.
Okay.
But we're just going to take the derivative, and we're not going to bother with all that. So let's do this problem. I want to find the slope of this circle, x squared plus y squared equals 25, that's a circle with radius 5, at 3, negative 4. So this is a circle with radius 5. I'm saying over here at, let's see, 3, negative 4, that's going to be down here somewhere. I want to find the slope. Right?
Mm-hmm.
So let's find the slope of the circle at 3, negative 4. And you can do it the way that you just barely said. Solve for y first, then find your derivative. That's perfectly fine. Or we could just implicitly differentiate this thing and then plug in our point and see what the slope is.
Okay.
So let's look at this thing. So implicitly differentiate. I'm going to take the derivative of both sides with respect to x. So what's the derivative of x squared with respect to x?
2x.
2x, right?
Mm-hmm.
2x plus, what's the derivative of y with respect to x, or y squared with respect to x?
Just 2y.
2 times y times dy dx.
Yep.
Right? You can think about this one if you want to. You can think about this as 2 times x times dx dx if you want.
Okay, that helps a lot better.
And dx dx is just 1.
Mm-hmm.
Okay. So 2x times dx dx plus 2y times dy dx is equal to
0.
0. Following that?
Yeah.
Okay. What are we looking for? We're looking for we're looking for dy dx. That's what we're trying to figure out. So, I'm going to move this over here. Okay, dx dx, that's the same as 1, so we just have 2x. Move that to the other side, so I have 2y times dy dx is equal to negative 2x. With me?
Mm-hmm.
Okay, divide both sides by 2y, so we get dy dx is equal to negative 2x over 2y, which is the same thing as negative x over y. Okay, but I was looking for the slope at the point 3, negative 4. So plug in 3, negative 4, and what do we get?
3/4.
Negative 3/4.
Positive, because it's a
Positive.
negative.
Yep. Positive 3/4. Good call.
You didn't find the derivative of dy though.
Here's dy dx.
Okay.
Now, plug in 3, negative 4, and you get 3/4.
Yep.
So the slope of the circle at the point 3, negative 4 is 3/4.
How do you know where to put your dx and then your dy in when you start out with the equation?
How do I know where to put my dx and my dy? Not sure I understand your question.
Where
So
do
the dy dx comes from taking the derivative of y squared. It's just using the chain rule. Look, let's go back and do one like this really quick. Let's go back and say that we were doing 2x plus 1 squared, right?
okay.
I have some function in terms of x squared. I'm going to call this inner function part y. Y is equal to 2x plus 1. So now I have y squared, right?
Mm-hmm.
What's the derivative of this thing now? The derivative of this thing is 2 times that thing times the derivative of the inside, right?
Yeah.
Which is the exact same thing as 2 times y times the derivative of y with respect to x.
Okay.
So it's just a chain rule.
But when you don't have it,
The,
When you
the
have-
whole point is we don't even care. Here we had a concrete example, so we had concrete numbers. Here we have it in general. Here I told you what y is in terms of x. Here I didn't. Who cares what it is in terms of x?
What do you? Okay, I see what you're saying.
Does it make sense?
like,
Y is some function in terms of x.
yeah.
Now, up here, what is y in terms of x? I don't know, and I don't care. That's the beauty of it. So if I knew exactly what y is, like right here, then I can calculate what that derivative is like this.
Okay.
Now, when I'm dealing with something like this, I don't know what the y is in terms of x.
Okay.
So I just know it's this thing. If you tell me, okay, y is actually 2x plus 1, okay, I can replace this with this. But here's what it is in general.
Okay.
Now you with me?
I think so. Yeah.
See, we don't want to figure out exactly what y is in terms of x. We don't want to go through that work.
Mm-hmm.
So we can't write it this way, we can only write it this way. But since all we're looking for is what the dy dx is anyways, it's enough. Okay, so I think we're getting it.
Yeah.
Yeah.
Let's do another one. So let's find dy dx when we have this expression right here. So take the derivative with respect to x on both sides. So start with the y squared. What's that?
2y times dy over dx.
Times dy dx is equal to
2x plus,
2x plus, okay, now we're in trouble.
yeah,
Chain rule. Derivative of the outside multiplied by the derivative of the inside.
Okay.
So the derivative of the outside is what?
Cosine.
Perfect. So we have cosine of x times y
mhm,
times the derivative of the inside.
Which is 1.
So times the derivative with respect to x of x times y.
Can't you solve that?
Yes, we can solve that. And we're going to solve that. I just wanted to break it up in pieces so that we weren't doing it all in one go. Because this is now a product.
Oh, okay.
That's why I wanted to stop and calculate this one separately. So let's look at the derivative with respect to x of x times y. Derivative of the first multiplied by the second plus derivative of the second multiplied by the first. So what's the derivative of the first?
1.
1 multiplied by the second
Y.
plus the derivative of the second.
1 multiplied by x, which is
No.
x.
What's the derivative of y with respect to x? It's the derivative of y with respect to x. We don't know what it is. It is whatever it is though.
okay, that's right.
And x.
Can you simplify that anymore? Or is
Why
that
don't
just
you
it?
know what it is?
Huh?
Why isn't it just 1?
We don't know what y equals in terms of x. Remember, y is secretly some function x. Y, if we were to solve for it, it's going to be something like 5x squared minus 7 plus 13x or something. We don't know. We don't know what y is. If we knew exactly what y is, we could take the derivative of that thing.
Okay.
But we don't know what y is. It's some function in terms of x, we don't know what. So what's the derivative of y with respect to x? It's the derivative of y with respect to x. We can't write it as some number because we're not sure what exactly y is in terms of x.
Okay.
Make sense?
Yeah.
Okay, so this is equal to, well, now I'll just replace this piece with this. So this is the same thing as times y plus dy dx times x. Y plus dy dx times x. Right? Okay, so I'm trying to get all the dy dx's by themselves. I'm trying to solve for dy dx. That's what I'm trying to solve for. So I need to get all the terms with dy dx on one side and all the terms without dy dx on the other side.
Okay.
So we have 2y times, you okay with me just using y prime instead of dy dx?
Yeah, I like that way better.
Okay, so 2y times y prime is equal to 2x plus y times cosine of x times y plus x times y prime times cosine of x times y. Right?
Mm-hmm.
Okay, just going to bring this term over here and factor out the y prime. So we have y prime times 2y minus x times cosine of x times y is equal to 2x plus y times cosine of x times y. Right?
Yeah.
Just move this term over and factored out the y prime. Okay, now divide both sides by this. And that gives me my y prime. So y prime is equal to 2x plus y times cosine of x times y all over 2y minus x times cosine of x times y. There
That's
it
your
is.
answer.
Mm-hmm.
Can't be simplified.
I don't know. I can see.
Just take out the 2.
No,
Oh, yeah, because that would apply to you.
because then we'd have to make the other one 1/2. And
That's a mess.
that's not much important. We can check with the author, see if you got the same thing. 2x plus y times cosine of x times y, all over 2y minus x times cosine of
Okay.
x times y. Okay, so next. Now we have this one. This time we want to find y double prime.
Okay.
All right, so let's find y double prime of that thing. So first off, taking the derivative of both sides, what do we get?
6x squared minus
6y
6y
dx.
times y prime is equal to 0.
Right?
Yeah.
Okay. And now, well, maybe let's simplify it a little bit. Divide through by 6.
What?
Yep.
What'd you say?
Notice I can divide through by 6.
Okay.
So we get x squared minus y times y prime is equal to 0.
Move over your x squared, right?
Sure, we can move this to the other side if you want.
I like that.
So I'll do y times y prime is equal to x squared.
Divide by
y
y.
by y.
Well, we're looking for y double prime.
Don't you have to find y prime in order to get y double prime?
No, we could implicitly differentiate again.
But would it be worth
Right,
it
you
to
have to
implicit?
show me how you do that. How
So
do you
yeah,
get y
now
double
let's
prime?
take the derivative of both sides of this again with respect to x.
Okay.
Okay? So notice this one's a product.
Mhm.
Mm-hmm.
Okay? And then that one will be nice and easy. So we have the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first
Over. No, that's division.
is equal to 2x.
2x.
Now we're solving for y double prime. So y double prime times y is equal to 2x minus y prime squared.
Or.
Right?
Mm-hmm.
Y double prime is equal to 2x minus y prime squared all over
Y.
y. There's y double prime.
Okay, it makes sense, but why not do it with x squared minus y times y prime equal to 0? Could you have done it in that way too?
Oh, they want to get rid of all the y primes. So we can get rid of all the y primes too. Let's follow through what the book does. So here's what y double prime equals. They want to get rid of the y prime, so let's get rid of the y prime. So come back over here, y prime is equal to x squared over y, right?
Yeah.
So now we can make that substitution over here. So this is equal to 2x minus x to the 4 over y squared all over y, right?
And,
Just plugging in this.
and then you can yeah.
Okay, get common denominator in the numerator. So we get 2x y squared minus x to the 4 all over y squared over y, right? Which is equal to, multiply by 1 over y, we get 2xy squared over y cubed minus x to the 4 over y cubed. Follow that?
Yeah.
And then factor out y squared top and bottom of this one. So we get 2x over y minus x to the 4 over y cubed, which is what the author has. So he didn't like leaving the y primes in there, which is fine.
Okay.
There we go. That's y double prime. Okay, 5. Next example, or last example. So here's some curve, some crazy curve, who knows what it does. Our job is to find the tangent to this curve and the normal to this curve at the point 2, 4.
What does it mean with normal?
The normal is perpendicular to the tangent. So if this is a tangent line, this is a normal line.
Okay.
How do you find that?
The slope of this is the inverse reciprocal of this slope.
Okay.
Okay, so let's calculate it. I'll start with our tangent line. Tangent line to this curve, so I need to know how this curve is sloping at this point to get the slope of my tangent line, right?
Mm-hmm.
So let's find that. So take the derivative with respect to x. What do we get?
3x squared.
3x squared plus,
That is
come on, what is it?
I forgot how to do. It's
3y.
3y.
Derivative, or y prime.
Times y prime, perfect.
There you go.
Derivative of the outside multiplied by the derivative of the inside. Minus, now we have to do a product. Right?
Mm-hmm.
So minus, we'll put parentheses here and distribute it after. Tell me what to write.
With the this 9 times negative x.
Ignore the negative.
Oh,
We'll
okay.
distribute the negative in at the end. So just take the derivative now of 9xy.
Wouldn't it be 9x times y?
9x times y. Derivative of the
Is just
first multiplied by the second plus derivative of the second multiplied by the first.
9
First and what's the
times.
second?
You can just look at 9x and y,
Okay.
right?
Okay.
Okay, so what is it?
Times y. Plus 1 times 9x.
Did he do that right?
No.
Yeah.
What did I do wrong?
What's the derivative of y
dy.
with respect to x?
Just y prime.
Y prime. It's not 1.
Isn't it 1 plus y prime?
1 times y
1
prime.
times y prime.
If you want to think about it that way, sure, which is the same thing as just y prime.
Yeah.
Look, for any function, y is a function of x. What's the derivative of y with respect to x? It's dy dx. That's what it is. If y is some function in terms of x, then dy dx is just dy dx. It is not 1. That's only the case, the special case, where y happens to just equal x.
Okay.
Okay. So, what was this term?
Y prime.
9 y prime, right?
Okay, I'm lost in.
Oh,
by the
it's
second.
9. Yeah, now I'm getting confused too. 9x times y prime. Derivative of the first multiplied by the second plus derivative of the second multiplied by the first.
Mm-hmm.
Say that again and I'll get it.
Derivative of the first
Okay.
multiplied by the second
Plus the derivative.
plus the derivative of the second multiplied by the first.
Okay.
Good?
Yeah.
Okay. There is our is equal to 0. Okay, now I'm going to get all my terms with y primes on one side and all the terms without y prime on the other side.
Okay.
Because I'm solving for y prime. So we have 3y squared times y prime, that's this term, minus 9xy prime is equal to minus 3x squared
Plus 9y.
plus 9y. Factor out the y prime, so y prime times 3y squared minus 9x is equal to 9y plus or minus 3x squared, right?
Mm-hmm.
And divide.
And divide, so y prime is equal to 9y minus 3x squared all over 3y squared minus 9x.
Can't you simplify that with 3?
Yeah, should have done that a while ago. Take 3's out of everything, and that's the same as 3y minus x squared all over y squared minus 3x, right?
Mm-hmm.
Okay, so now we're saying at the point 2 comma 4.
12 minus...
Is that the
so
tangent
8.
or the normal? The derivative? Or
That's going to give me the slope of the curve at that point.
So that's...
Y prime gives me the slope at a point. Pick a point now. 2, 4, that's a point on the function.
how are you gonna find the normal?
Just need
Let's
each
just
other.
start with the tangent, then we'll calculate the normal.
Okay.
The tangent's 4 over 5, I think.
So we're looking for the slope of the tangent now. So the slope is equal to 3 times, where's our point? Our
12
point's right
minus
here.
4.
So 12 minus 4 all over
16 minus 6.
16 minus 6, right?
Mm-hmm.
So we get 8 over 10, which is 4/5.
Okay.
You do that right?
Yep.
Yeah.
So that's our slope of our tangent line.
Okay.
What's the equation of our tangent line? The equation of a tangent line is y minus y1 is equal to m times x minus x1,
Mm-hmm.
where y1 and x1 are the points that we know it goes through. So we know it goes through the point 2 comma 4. So y minus 4 is equal to 4/5 times x minus 2. This is our tangent line. So maybe y sub t for tangent, to keep track of the fact that that's our tangent line. And our normal line goes through the exact same point, it just has a negative reciprocal slope. So y for our normal line is equal to negative 5/4 times x minus 2.
So it's just negative 5/4, right?
Yes, for its slope. And so now we can solve both of these to figure out what exactly these lines are. So for a tangent line, we get y of our tangent line is equal to 4/5 x minus 8/5. That's distributing that to that.
Okay.
Plus 4, or plus 4.
Okay.
Right?
Mm-hmm.
Yeah.
So this is equal to 4/5 x plus 12/5.
Okay.
For our tangent line, our normal line is equal to negative 5/4 x plus 10/8. Right? And then we need plus 4. Plus 4, if we write that in terms of,
Right, in terms of 8, it's 36.
oh,
Sorry, 32.
my ear is driving me nuts. Well, 10/8, that's the same thing. That can be rewritten for us. So we'll just write it as 16/4.
Okay.
Right? Which is equal to negative 5/4 x plus, so this is 5/4 plus 16/4 is 21/4.
Why did you multiply the denominator by 2 as well? So wouldn't it be 10?
Because I'm being crazy. Thank you.
Okay.
Okay.
Which is 26
Thank you.
fours.
What did I do? Yeah, don't let me do that. 10/4. Yes. Wow. That was terrible. Okay. 10/4, which is the exact same thing as what? 5/2.
Mm-hmm.
So we have 5/2 plus 8/2 is going to be 13/2. Did I do that right?
Yeah,
Better make sure.
26 fours is equal to 13/2.
Okay. So there we go. There's our normal line.
Okay.
Okay. That's it. 4 sections.